This is the second of the 6 video series on x86 assembly language. Capitalizing on the powerful move instruction from the previous video, we will look into the rich set of addressing modes of the x86 architecture. This is the content that we will be looking at in this video. We will start off with the basic addressing modes and try to understand them through an example using a swap function. The video then talks about the difference between 32-bit versus 64-bit implementations. And lastly, the complete addressing modes are revealed with a little quiz at the end. So let's look at the various ways we address memory. These are the basic addressing modes. There are many addressing modes of x86 architecture, and we are going to look at all these modes later in this video. The first addressing mode is called register indirect, which says that the register contains an address, that we are going to use the contents of the register as an address to memory. As we said that memory is just an array, so we index into the memory through the content of register R. As an example, here we have ECX in the parentheses on the source side, which means that we need the contents of memory location specified by the address in register ECX, okay? So by now we must have familiarized ourselves with the concept of a load store operation, right? The other type of address mode is called displacement and is specified by the format D with R in parentheses. The register R specifies a memory location, but the final effective address is computed by adding the contents of the register with the displacement D that specifies an offset from that memory address. For example, we use the instruction MOVEL 8 with EBP in parentheses, comma, EDX, which means add 8, that is an offset to the contents specified by the base pointer, and load the results in register EDX. Remember, we said that the base pointer is a special purpose register that is used in addressing the stack region of the memory. So we will see a lot of these instructions and we'll get to know this very well over this series of videos. Let's understand the basic addressing mode using an example swap. So here we have the C function swap from our earlier programming semesters, right? It does the following. It takes as parameters 2 pointers and gets the values of xp and yp and stores them into local variables t0 and t1 respectively, okay? And then stores memory address location pointed to by yp and store in the location pointed to by xp. So essentially that is swapping the contents of locations addressed by these pointers. So the assembly version of this function is basically composed of these 3 blocks. One is called the setup, that is used for setting and reading the parameters and setting up the stack and so on. And we also have the finish block where we restore the stack to its original location, restore register values, and then we also need to return back to the caller. And then we have the actual execution block, the body of the function. That is the main computation we want to perform. So every function has a start and finish blocks. So let's see how stack works. Let's go step by step. So this is our swap function from the previous slide and the body that we are going to focus for now. So this is the mapping of registers to variables that is performed by the compiler. So compiler chooses this mapping plan, okay? According to this mapping, YP happens to map into ECX and XP is mapped into EDX. T1 and T0 are mapped into EAX and EBX respectively. And this is the state of our stack in the beginning of our execution. It goes from lower to higher addresses, and it is just a matter of convenience which way you draw the stack from lower to higher addresses, either from bottom to top or vice versa. You just have to keep in mind that this is a stack and the functionality of the stack. A good way to visualize and remember this order is through the contents it contains. The parameters that also includes the return address are placed above the old EBP towards the higher addresses. And the local variables are placed below the old EBP towards the lower address space. We will come back to these calling conventions at the appropriate time. For now, just remember, and I will repeat, that these are the locations in stack for passing parameters to the function. And the locations below 0 are for local variables relating to that function. And also that this is the state of our stack in the beginning of the execution. Okay, now we are ready to see how does this code execute step by step. So here we have our registers. Recall that XP and YP are addresses. So XP points to the location 124 hexadecimal, which contains the value 123 in decimal. And YP points to the location 120 in hexadecimal and contains the value 456 in decimal, right? And we want to swap these values or the contents of these addresses pointed by XP and YP respectively. Just make one distinction in these slides, that whenever we refer to memory location, that is going to be in hexadecimal, and the contents in these locations would be in decimal. Okay. In this example, the displacement-based addressing mode is used to access the memory. So basically, what does the first instruction say? Well, it says since YP is stored 12 bytes away from the EBP, so add offset of 12 to the base register EBP to compute the effective address of the memory location we want to access. And, or more precisely, the second parameter of the swap function. Please note that these offset values are predefined number of bytes that indicates the order in which the function parameters are loaded onto stack. These parameters are pushed onto stack in a reverse order from right to left. That is the reason why we get the last parameter farther than other parameters. And since the cells depicted in the stack are 32-bit wide memory locations, thus the memory addresses of the cells are 4 bytes apart. So what this instruction does when executed, since the source is a memory reference, it basically obtains YP from the memory and moves the value of YP into ECX. This also highlights the concept. This also highlights the concept of a CISC machine, a complex instruction set computer that has a complex instruction format. And this is what is meant by being complex. The instruction has multiple operations that are performed in a single instruction. It includes calculation of the offset of the effective address, a memory reference, and an assignment of a value into a register. So that is the reason why load and store instructions are classified among complex operations. Okay, and we do the same thing for XP, but since XP is stored 8 bytes away, we add 8 to EBP and load 124 hexadecimal value to the register EDX, as can be seen on the screen. So now EDX holds 124, which is the address held by the pointer XP, and ECX is holding 120, that is the address held in the pointer YP. Okay. So what we want to do now is store the contents of the pointer YP into EAX. But remember, we just have put YP into ECX. So if we just use parentheses around ECX, we are actually getting the address. We are getting the address pointed to by YP. Since YP is pointing to the address location 120, the contents at that location is 456, which is loaded into EAX. Okay. Similarly, if we put parentheses around register EDX, which contains the address location pointed to by XP, that happens to be in EDX, and when we execute this instruction, we get the contents at that location, and and load it into register EBX. Simple enough, right? Now we do the swap. So we take the contents of EAX, that are the contents of the locations in memory pointed to by YP, and store it into XP because we are swapping, right? And we still have the address of XP in EDX, and by placing a parenthesis, it becomes the reference to memory. And since it is the destination, so what actually happens is that the value of the address pointed to by XP gets updated with the contents of EAX. The same thing happens with the contents of EBX that holds the contents of the pointer YP. We take the contents of the EBX and put that to the location specified by ECX, that is holding the address pointed to by YP. And since the memory reference is a destination, that is why it is a store operation, and the location pointed to by YP gets updated. Now let's pay some attention to the x86 64-bit architecture and see the swap function implemented on this architecture. So the x86 64-bit has 16 registers. Just like in 32-bit version, some registers are special purpose, but there are a lot more general purpose registers. So the 32-bit registers have been extended with a wider register size and 8 new 64-bit registers that can also be addressed in multiple word sizes. Remember that in 32-bit we used L, that refers to 4 bytes. In 64-bit we have 8 bytes called quad word. So the move L refers to moving 4 bytes worth of data. Now the 64-bit architecture, we replace the L with a Q that is 8 bytes or 64 bits long. And similarly, all other instructions now uses a Q at the end. Also note that the x86 64-bit architecture can still use 32-bit instruction that generates 32-bit results. The higher order bits of destination simply are set to 0. Okay. Again, confusing historical term word, which is not the machine word size. Okay. Here is the swap example that we saw a few moments earlier. Remember that we were reading the 2 pointers, XP and YP, from the stack, because the IA 32-bit architecture is designed that way, and the parameters are passed by the stack. And also note that we have used the move L instruction because we are moving 4 bytes worth of data. Now let's look at how the code would look like in 64-bit machine. Okay, first thing to note is the move L, because the input parameters are of type int, right? And also note that we are passing the parameters via the registers. The first parameter XP is stored in RDI, and the second parameter YP is stored in RSI. And these are 64-bit pointers because addresses in the IA 64-bit architecture are 8 bytes long. And how interesting to see the same code get implemented in just 4 move instructions, and we do not need the stack setup and finish stuff that was a requirement in the 32-bit version, right? We are no more reading the parameters from the stack, which is a big advantage as the load store memory operations are expensive. So the IA 64-bit architecture are much faster. You don't have to store it to memory and read it back, okay? And we have much fewer instructions that would impact the size of the assembly code. The first 2 instructions loads the content of XP and YP into registers EDX and EAX respectively. And the next 2 instructions simply swap these registers into the required memory locations. And that's it. maybe it is simpler because you don't have to use the stack at all. No stack operations required. And also note that we are still moving 32 bits worth of data. Why is that? Why are we still moving 32-bit worth of data? That is because our parameters are integers, and integers are 4 bytes long, right? Suppose that we had long int, and since long int are 8 bytes, so now we have to use a queue instead of movl, right? Remember the simplest form of addressing used in move instruction for accessing the memory, where we used a register in parentheses that is interpreted as the address of location in memory. And we saw a lot of this kind of addressing in the swap function. So the most general form of addressing a memory is a combination of this D, RB, RI, and S. D is a constant displacement, also called the offset, and the value can be 1, 2, or 4 bytes, something that is added to the final result here. RB is the base register. Any of the 8 registers or the 16 registers in the 16-bit architecture. It is called the base register because we are adding to that reference here. We are adding to that reference point, that is the base register where our reference starts. RI is the index register. It is used for things like arrays, and that is why we are multiplying here by the content of RI. Okay, that is multiplied by the constant that is called scale. So scale can take 1, 2, 4, or 8. Why these numbers? Because we want to officially support arrays of values of these sizes. There are many ways of using a combination of these parameters to make a variety of addressing modes. For example, if you just use in parentheses RB and RI, the final address of the memory is going to be the contents of RB added to the contents of RI. In this case, the S is 1 and D is set to 0. You can also use D, RB, RI, and that is just going to do RB plus RI plus D. The scale here is just set to 1. And also, you can have no displacement at all, just the RB, RI, and S. In which case, D is 0, and the final address will be RB, and the final address will be RB with the scale multiplied by register RI. So let's try this example here. Suppose that we have 2 registers in this example, EDX and ECX, that are set to F000 and 100 in hexadecimal values respectively. And the addressing modes are given on the right as a reference to solve these address computations. Pause this video here and try to solve it yourself and see if you can use these special cases here. And here are the results. So this is all for this session, and we have stretched our arms good enough to take on instructions for the arithmetic and logical operations in the next video.